What's going on, everybody? Welcome to another video where we discuss machine learning / statistical learning topics. The topic for today is pretty interesting. We're going to go over how to properly assess your model's performance after training it, and we'll be using sklearn's train test split, which is pretty popular, but it definitely has limitations unless we use it correctly. So we're going to use the Auto-mpg dataset, which concerns fuel consumption in miles per gallon, to be predicted by both discrete and continuous attributes. And as you can see, I have the data set pulled up over here. And what we're going to do is we're going to turn this into a binary classification problem by creating a variable. We'll call it mpg01 or something. And this variable will take on the value of 1 if the miles per gallon is above the median, and then it'll be 0 otherwise. And so we'll go ahead and calculate the median miles per gallon. We'll just use NumPy, and this should make it pretty straightforward. And then we'll create this new column. We'll call it mpg01, and it'll be based on the current miles per gallon column, and we'll just apply lambda x. It'll be 1 if the median mpg, actually if x is greater than the median mpg, and then it'll be 0 otherwise. And we can take a look at our updated data set. So as you can see, we created a new column called mpg01. And the nice thing about this new variable is that it's going to ensure, because we use the median, it ensures that our data set is balanced. So that won't be something that we'll have to worry about. For the purposes of today's topic, we're going to be using cylinders, displacement, and weight to classify observations as having miles per gallon either below the median or above. So we'll go ahead and set up our design matrix, which will, the first column in our design matrix is going to be a bunch of 1s, and then the other 3 will be cylinders, displacement, and weight. Our response variable is going to be this new binary variable that we created, 0 or 1. And we'll go ahead and split our data into xtrain, xtest, ytrain, ytest using sklearn's train test split. We'll pass in a test size of 0.3. A 2/3, 1/3 split is optimal when deciding on a test set size, and there are reasons for that. Maybe we'll cover it in another video. But let's say that you are looking to fit 2 competing models. So we'll use logistic regression, which is a generalized linear model, and then we'll also use KNN, which is a non-parametric modeling technique that produces class estimates based on a defined distance metric. And the flexibility of KNN is actually determined by the neighborhood size, which is its hyperparameter. So if you choose a neighborhood size of 1, the model is highly flexible, which means that it has high variance and low bias. Again, we can discuss the topics such as the bias variance trade-off another time. But for now, what we're going to do is train and test both models and then see on average which one performs better. So make sure that you're using the same split for both models. We'll go ahead and instantiate our logistic regression model. We'll fit it on xtrain, ytrain, and then we'll predict on our test set, which is 30% of our data, and then we'll calculate the accuracy, and the accuracy is going to be basically on average how often were we correct. So how often did our predictions match the truth, and then we'll take the mean of all of those, and then we'll also fit KNN. By default, the neighborhood size is set to 5, so we'll just leave it at that. But that usually is a hyperparameter that you'd want to tune. We'll go ahead and fit KNN. We'll get our predictions on the testing sets, and then we'll calculate our accuracy in pretty much the same exact way that we did for logistic regression. And after fitting, we'll just go ahead and calculate the accuracy. So for logistic regression, GLM test sets accuracy. And then we'll print the same thing for KNN. Test set accuracy, and that'll be over here. All right. So if we look at the accuracy of both, it seems that logistic regression is getting 93% accuracy. about 3% higher than that for KNN. But what's really interesting about this is if you go ahead and run the code again, both accuracies change. Now they're more equal, and if you keep running it, that test set accuracy keeps varying, and that's actually the issue with using a single split. Our estimate of the test set accuracy is highly variable because it depends precisely on which observations are included in the training set and which are included in the testing / validation set. So what we'd want to do is we'd want to get a bunch of different test set accuracy estimates so that we can assess how much uncertainty is in there. Maybe we take the mean and use that as our best estimate. Now, a good solution for that would be using something like k-fold cross-validation, which is a great solution because the procedure of training / testing is repeated k times, and each time a different group of observations is used for testing, and so you end up with k estimates of the test accuracy, and you can average them for a better and more reliable estimate. Now, other than using k-fold cross-validation, what you could do is keep our setup, but just run it, say, 200 times, and then we can create an accuracy matrix. So we'll create a matrix of shape 200 by 2 columns to keep track of both logistic regression and KNN, and 200 to match the number of iterations. And then we'll loop for j in range iterations. We can pretty much copy and paste our code here. Make sure that you are splitting your data inside the loop. And also make sure that you're not setting a seed. If you set a seed, you're taking out the randomness. But through each iteration, we're getting a different split of the data, and we'll record our accuracy in this matrix. So it'll be j, 0 for logistic regression, and then for KNN, it will be, let's see, j, 1. And then we'll go ahead and run that, and it should run pretty quickly, in 1 second. And then after this, what we'll do is we'll set up side-by-side box plots to get the distribution of all of the different test set accuracies that we've collected. So actually, first thing we'll do is we'll turn our accuracy matrix into a pandas data frame so that it's easier to work with. And the columns are going to be, we'll have 2 columns, one for logistic regression, one for KNN. We'll set up our figure. We'll do a fixed size 10,6. And then we'll go ahead and set up our box plots. So x will be the variable, y will be the value, and the data is going to be, we'll just need to melt this or pivot it so that we can actually do the box plots. So we'll set up a dart grid, and then we'll do plt.show. All right. So what you see here is the distribution for both KNN and logistic regression of all the different test set accuracies that we've collected. And this is really helpful because, as you could see, for GLM, for example, on certain splits of the data, you're getting accuracy as high as 0.94 or as low as 0.81. And what you'd want to do is take the mean of all these estimates and see which one performs better on average. But it's also crucial to look at the standard deviation of these estimates, right? Maybe KNN performs a little bit worse, but it varies way less than logistic regression, and that might be a good trade-off for you for your specific use case. That's obviously not the case here, but in general, doing that is good practice. And it also seems that there's quite a number of outliers on these. Let's see what happens if we run this one more time. Seems to disappear for logistic regression, but it's still there for KNN. But the point is, make sure that you're getting that you're testing your model on many different splits to get a better idea of how well your model's performing. You could just get a really lucky split for logistic regression and think that your model has 95% accuracy, which is not true. But anyway, I hope you enjoyed watching. If you have any comments or suggestions, feel free to drop them in the chat. Otherwise, I will see you all next time.